Depletion approximation, you know we make it in p-n junctions, metal semiconductors, very common approximation. Why does it work so well? So, let me show you something here. It's not, right now, no depletion approximation. I'm showing you a graph. Take a look at this graph. Some y-axis, x-axis. Okay? This is a constant region of about 0.14 micron. And then this is a transition region of 0.14 micron. It's a mathematical curve. Now, if I tell you somebody takes this mathematical curve, approximates it like this, how good do you think the approximation will be? Huh? Somebody takes this. This is what the nature of the graph. And somebody says, well, I'm going to approximate it like this. How good do you think is the approximation? Good or bad? Bad. All of you will say bad approximation, right? How can you, the transition region that you're talking about is as large as the constant region. The transition region where it's changing is as large as the constant region. How can you throw it away? How can you neglect that? Okay? How can you neglect that? And then work on this particular basis? Well, does it remind you of something? You can guess where I'm headed? What does this look like? Constant and like this? Depletion approximation, does it look like that? And this looks like something of this sort? Let me remind you, okay? So, how good is this approximation? I'm sure everybody who looks at it will say it's a terrible approximation. It's a terrible approximation? All right, fine. Okay, let's come back to our p-n junction. P-n junction, we know that there is a space charge region here. Space charge region here. We draw all of us draw a nice line here and a nice line here. We know boundaries are never sharp. They're never line, boundaries are diffuse. So if I look at the charge on this side is the donor density here. And the charge, if we plot it like this, but we know that the charge starts to fall gradually to zero. The boundaries are not sharp. The reason why the boundaries are not sharp is electron density here is Nd. The electron density, as you enter the depletion region, the electron density starts to reduce and becomes smaller and smaller gradually. And therefore, the boundary of the depletion region or the space charge region is diffuse. It's not constant here. There's a transition region here. It doesn't fall from, charge doesn't fall from Nd down to zero here. Similarly, it doesn't start from Na and fall to zero here. It falls gradually. So that's the more accurate picture here. And what we are doing in depletion approximation is we are looking at this, yes, we are looking at all of this region here. And typically with the depletion region, or space charge region, we solve a Poisson equation, we write down charge. Charge is due to ionized donor atoms, ionized acceptor atoms, holes and electrons. And what we say is, well, the problem that becomes for us is that hole density is an exponential function of potential. Electron density is an exponential function of potential here. And if we put exponentials here into this equation, the equation becomes complex. And we say, well, let's ignore the n and the p, right? We say over most of the region, n and p is much smaller than the background doping, right? And then we approximate it as, we neglect p and n, and we approximate it as ndx minus na minus x. That's a standard depletion approximation, right? As I said, the reason why we are doing it is the whole equation becomes nonlinear. You have exponentials, analytical equations become almost impossible. And when you would ignore all of that, then all of you have done these calculations and all that here. So you end up with this. You end up by saying my charge density rho is QND. Charge density rho is QND. Here drops to 0 at xn. Charge density is QNA, drops to 0 at xp. You simplify it. Obviously, you know that it's not sharp, as I said. It's not drops to 0. It drops gradually to 0 here. Okay? And based on that, you calculate electric field. You calculate W. Depletion means all kinds of things you calculate, right? You calculate capacitance, and you use the capacitance to calculate doping, all kinds of things that we do based on this approximation. Extremely important approximation, right? We use it regularly. And depletion approximation you will use not just in PN junction, you'll use in BJT, HBTs, you'll use in thyristors, JFETs, MOSFETs, Schottky diodes, MESFETs, HEMT. Every device you're using it, depletion approximation. So it's central. It's central to semiconductor devices, this depletion approximation. And we're deriving equations and using those equations to calculate maximum electric field, capacitances, all of that based on that approximation. So when so much depends on that approximation, it's good to see how good is this approximation. Well, one answer is, well, a lot of people are using it. It must be pretty good. Otherwise, they would have gotten rid of it. If an approximation is not good, people would have gotten rid of it. If everybody is using it, it must be good. It must be a good approximation. But my job here is to ask, to go deeper. If it is good, why is it so good? What is the reason that the depletion approximation is so good? So this is the point that I raised here. So this is the actual charge density inside a space charge region. See, more accurate word for all of this is, I would rather not call depletion region, call it space charge region. Okay? Space charge region is a more accurate word. There's a region where you could say is more like depletion region. So this is the space charge region here. That's what it looks like. And this is the approximation. So actual space charge region has a part which is relatively constant and has a part which is sort of decays to 0 here. As I said, the boundary is not abrupt. The boundary is not abrupt. It's gradual. Now, how good is the depletion approximation? Well, the same thing that I showed you, a mathematical graph. How good is the depletion approximation? Your natural question, your natural answer that will come to your mind is it will be good if this region here, this transition region length, LT, is much smaller than this particular length. If the transition region is very, very narrow, it's okay. Transition region is very narrow. I neglect it. I approximate it by a vertical line. That's the natural thing that will come to your mind. If the transition region is very narrow. The next question is it really very narrow? How narrow is the transition region? And is the transition region negligible compared to this? Then I would be fine. Okay? Well, what do the experts say? Let's come back. Let's do some book bashing. Okay? So common belief is that here. So let me put. By the way, how large is this region here? If you go and, many textbooks will talk about it. If you analyze this, there's a concept of Debye length. There's a concept of Debye length. And on that basis, we can calculate how large is this region. It's about 3 times Debye length. So Debye length has this expression here. Any textbook that you pick up, you'll find discussion of a Debye length. Okay? Pick up Z's book, pick up any of them. So LDN is ES KT Q square ND. It's a Debye length. And so this is the transition region length, 3 times LD. Okay, 3 times Debye length. So you have a transition region which is 3 times Debye length here. You have a transition region which is 3 times Debye length here. And then you have this region here. Okay, so we can derive this. So the issue is this negligible? All right. Now note that what happens here. If I look at if I look at this 3 LD here and 3 LD here, total transition region width comes out to be 6 LD. And 6 LD, if I divide by W, what I find is 38.5%. So transition region width is not negligible. 38.5, close to 40%. Close to 40%, which actually what it means is, I will show you actual simulation results. This region length is almost as large as the region length here. The constant region is as large as the transition region length. The constant region is as large as the transition region length. Right? So how is everybody throwing that transition region away? If the constant region and the transition region are almost the same, and I'm just ignoring it, I'm throwing it away. And then everybody is making it. Everybody is making depletion approximation. And it must be working very well. So how is it working very well? That I can neglect this entire region, which is as large as this, maybe. I can neglect it and still it works so well. How does it work so well? Why does it work so well? All right, so this is sort of the mystery which is there. If you go deeper into it, you find that this is what is happening. So what do the experts say? Well, the experts are all talking about, they're saying that yes, the transition region is equivalent to a few debye lengths. For example, this is a very well-known book. When I was a graduate student, I learned my semiconductor devices from this particular book, Mueller and Kamins. They're talking, again, same thing, that the carrier density is reducing in the transition region. It's over a few debye lengths. And they say the depletion approximation, look at what they're saying. They're saying LD, the debye length is 40 nanometer. And they're saying XN is the amount of depletion width on the N side. They're saying XN is 210 nanometer. All right? They're saying debye length is 40 nanometer. And the depletion width on the N side is 200 nanometer. What is the total transition region length? As I said, 3 times LD. So the total transition region, according to them, is how much? 120 nanometer. How is 120 nanometer negligible compared to 210? But they say the depletion approximation is reasonable. How? How is it reasonable? 120 nanometer of transition region length and 210 is the depletion. How is it reasonable? Well, that question is not being raised. Nobody is asking that. How is it reasonable? Okay? As I said, if I look at the boundary layer that they're talking about, divide by depletion, which is almost 57%. How is it reasonable? Well, this was a professor here, Moll, all of you remember Moll, Ebers-Moll? Ebers-Moll model is because of this. He's one of the giants of semiconductors. So they're talking about, all this depletion region. They're not talking in terms of length, but they're talking about in terms of potential. So they're saying there's a potential drop here. From here to here, there's a potential drop in the transition region. And they're saying potential drop is how much? 4.6 times KT, VT, KT by Q. And they're saying it's about 0.12 volt. They're saying it's about 0.12 volt, and the remaining drop is here. And they say depletion approximation is valid when the total potential drop across each side is larger compared to this value. Okay, so now let's pause. And they say it's okay. So let's pause. The total drop, let's say at 0 bias, the total drop built-in voltage is, let's say, 0.8. On one side of the junction is 0.4. So it's 0.12 versus 0.4. 0.12 is the drop in the transition region, 0.4 is the total drop. How is it negligible? It's not. This is another book, David Rulston. As I said, in most of these cases, you will find what they're saying is depletion approximation. They're all implying, let me tell you, they're all implying that the transition region is not too large compared to the depletion width. And that's why the depletion approximation is working fine. Most textbooks, so what I'm trying to point out is most textbooks seem to imply that when W is much larger than LT, the depletion approximation is okay. The depletion width is much larger than the transition region length. That's why we make it. They also seem to imply, this is very important, they also seem to imply that depletion approximation that I'm making, it refers to region 1. That when I make depletion approximation, actually I'm neglecting region 2. So what the implication is, almost all the textbooks that you read, almost all the textbooks that you would read, what they would say is, depletion approximation that they're trying to imply, if not explicitly they're stating, but they're implying that depletion approximation is saying that this region is the region 1. And you're neglecting region 2. And obviously, if you're neglecting region 2, they're saying this length here has to be much smaller than this length here. And they're saying, well, it is. Sort of brushing it aside, and they're saying it is. And I showed you with examples that according to the numbers that they are quoting, it is not. It is not. Okay? All right, let me show you doing some simulation. So, simple case here. a PN junction with doping of 5 times 16 and 5 times 16. Just to simplify, symmetrical junction. Okay? When you simulate, this is the charge density you get. Symmetrical, both. This is the N side and the P side, the charge density that you get. Let me go and show this in more detail. So I'm plotting charge density on one side. This is how charge density goes. Starts from here and then gradually goes to 0 here. Okay, this is the exact charge density that you will get if you don't make any approximation. Exact charge density that you get here. So I'm looking at the 90% point, the place where the charge density falls to 90% of its value here. And then I'm looking at the 10% value here, right? To look at how large is the transition width. I'm not making any approximation. I'm not talking about Debye length, LT, 3 types, nothing, okay? So what I find is the following. 90% point is where? At 70 nanometer. And 10% point is where? At 130 nanometer. How large is the transition region? 130 minus 70? 60. How large is this constant region? 70. 70 or 65, right? The constant region is how much? 70. The transition region is how much? 60. How can you neglect it? How can you neglect this? But we are all neglecting it, right? We are all neglecting it, but is it so straightforward that you can neglect it? The transition region is very small, and therefore you can forget about it. Transition region is 60 nanometer, and that's about, if I calculate Debye length, that comes out to be 3 point, as I've been saying, 3 times LD, 3.3 times LD here. It comes out to be to that. So, all right, LD is here. So this is charge here. So if you are saying, if you are neglecting the transition region, if you are neglecting the transition region, does it mean that you are neglecting all this charge here? Does it mean that? You're neglecting the transition region. So are you neglecting all this charge? Total charge, total charge in the space charge region, if you integrate, this is here. How much is this charge? If I calculate the charge, amount of charge here versus the total charge here, it turns out to be that you're neglecting 38% of the charge. Q transition versus Q constant, 38% of the charge. So if you say that I'm neglecting the transition region and I'm neglecting all of this charge here, you're neglecting 38% of the charge. All right? Now this is sort of this thing here. This is sort of interesting because if you're neglecting so much charge, 38% of the charge if you're neglecting, you should have a lot of errors, right, in your calculation. For example, we estimate electric field. How do we estimate electric field? We take Poisson's equation, and what do? We integrate. We integrate the Poisson's equation, which means you are integrating charge. So if I'm neglecting 38% charge there, I should have a lot of error in my, let's say, the peak electric field. And how much error do I really get? Well, if I calculate from simulation versus the depletion approximation, the error is only 4.4%. So depletion approximation gives you an answer for maximum electric field, and accurate simulation gives you an answer. If I compare the two, the answers are different only in 4.4%. Depletion approximation is working very well. But how did I get that answer? I got that answer by integrating. But then you are saying in depletion approximation, I'm neglecting transition region. And the transition region holds 38.5% of the charge, right? If I'm ignoring 38.5% of the charge, why am I getting 4% error? That's the mystery. Why is the depletion approximation working so well? If you're ignoring the transition region holds 38% of the charge. And electric field you get by what? By integrating. Integrating the charge. And this error of only 4%. What is really going on? I'm not disputing that you're ignoring. That's what everybody is implying. Well, it's not just about electric field. I can look at capacitance. I can calculate capacitance from the formula, depletion approximation formula, and I can calculate capacitance using simulation. Let's say if I look at capacitance as zero bias, I can calculate both. The error is around 4%. So depletion approximation, that's why I'm saying, that's why, everybody's using it. Depletion approximation is working very well. You get 4% error, which is fine. For an analytical expression, 4% error is pretty good. They're pretty low. That's why everybody's making it. The question that I'm raising is, if you're ignoring the transition region, which is as large as the constant region, why is this approximation working so well? It appears as if you're committing a large error. 38.5% of the charge you're ignoring, right? But the error that you're getting is 4%. How is this working out? Well, nobody's really talking about it. Nobody talks about why depletion approximation works so well. And for you guys who are interested in modeling, you'll see something very interesting here. Why depletion approximation works so well. I'll not go into the details, but this is the charge. The black line shows you the actual charge density. The red line that you see here is obtained from depletion approximation. Depletion approximation, W I can calculate, and if I draw W, depletion approximation is doing this. What is the first thing that you notice? Depletion approximation is not saying that we are only taking this part. Look what depletion approximation is saying. Depletion approximation is giving you a space charge region width which is from till here. Till here. Now something very interesting occurs. What does depletion approximation do? Look at the depletion approximation is very accurate here, right? It coincides, very accurate here. What happens here in this region? Depletion approximation is erroneous, right? But what kind of an error? Depletion approximation is overestimating charge, correct? Overestimating charge. In this region, depletion approximation is saying there's no charge, but there is charge. So what are you doing? Underestimating charge. So you're overestimating charge here, and you are underestimating charge here. And all the results that you obtain from Poisson's equation, you obtain by what? By integrating. By integrating the Poisson's equation. So you overestimate charge here, and you are underestimate charge here, and what happens? The two errors cancel each other. The two errors cancel each other, and you get a very accurate result. There's a mutual cancellation of errors here. There's a mutual cancellation of errors that occurs here, and a mutual cancellation of error occurs here, and you get a very good result. 4% error here. So there are two messages here. First is depletion approximation is not just this constant region. It's actually taking the entire charge, space charge region, and approximating it by a rectangular. It's not neglecting the transition region. In fact, it's taking the transition region also, and part of it is approximating it by a rectangular. And overestimating charge here, underestimating charge here, and they mutually cancel each other and result in a drastic reduction in errors here. So the real reason why depletion approximation works is not that the transition region length is much smaller than that. That's not the reason. Transition region length, as I've shown you, if you go back here, right, transition region length is, we can see here, right, transition region length is as large as the constant region length. But there's a very interesting thing that is happening is there's a mutual cancellation of error occurs. That's why the approximation is working so well. All right. So in modeling, when you're modeling something, it may look like a very bad model, right? You're totally neglecting it. But if you could arrange in some form that a mutual cancellation of error occurs, a apparently bad model may give you just what depletion approximation is. It looks like a bad model. You're altogether ignoring, it appears as if you're altogether ignoring the transition region length. That's what most people who talk about depletion approximation tend to imply, that you're ignoring the transition region. right? So a bad approximation gives you a good result here. So let me stop here.